Okay, we need to finish section 3.2 on direct proofs. So just a recap of where we left off, we showed that if n was an odd integer, then 4n cubed plus 2n minus 1 was odd as well. And so I just put a little highlights of what we did in the proof. So we assumed n was odd. A direct proof, you assume the hypotheses. So n was odd, and that meant by definition n was 2k plus 1 for some integer n. And then what we do, we took the 4n cubed plus 2n minus 1, we substituted 2k plus 1 n for n, and then we did some algebra, and we worked it all out, and we got that we could rewrite this as 2 times some integer plus 1, and that's the definition of odd, which meant 4n cubed plus 2n minus 1 was odd. So that was just the rough idea of our proof, the high points. Now the next result, they want us to... in the book, they go after this proof, they explain it's called proof analysis of result 3.6 on page 87. So they notice things about this proof, and then they redo it in this next result. It says if n is an integer, then 4n cubed plus 2n minus 1 is odd. Notice in our previous result it assumed n was odd, and in this result it just says n is any integer. Okay. So, I mean, it made sense to let n be 2k plus 1 because they told us n was odd. But here, n is just any integer. Now, what they do in the proof analysis is they make you realize that we have an expression minus 1. And remember I said you could use, for the definition of odd, n is 2k plus 1 or n is 2k minus 1. But be consistent within a single proof. And notice I have something minus 1 here. And so there's a 1 waiting for you in the definition of odd, so maybe we don't have to do what we did here. So let's do this proof. Okay, so it's a direct proof, so we assume the hypothesis if n's an integer, so let n be an integer. Okay, period. Don't say too much in the first step. Notice, right now we're kind of stuck, because in the previous proof we assumed n was odd. That gave us n was 2k plus 1, and that sort of begged you to substitute into the expression. But here we just have n's an integer with no structure on it at all. However, we don't need it from what I said before. Let's look at 4n cubed plus 2n minus 1. Again, to show that this is an odd integer, we need to write it as 2 times an integer, either plus or minus 1. I'm going to stick to plus 1 just to show you the game I'm going to play here, because you use this technique in other proofs. Okay, so let me rewrite this. This is 4n cubed plus 2n. Now, how can I rewrite negative 1, but I want to get a plus 1 at the end? If I put a plus 1 at the end, because I want to use the odd as 2 times something plus 1. But notice these aren't equal anymore, so what do you have to do? If this is negative 1, how do you get a negative 1 out of that? You put a negative 2 here. So negative 2 plus 1 is negative 1. And again, a reader going from here to here, they may not understand why you did that, but they're going to know that negative 1 is negative 2 plus 1. Now, why did I do that? I'm continuing with my equality here. I can factor a 2 out of the first 3 terms. So 4n cubed plus 2n minus 2 and then plus 1. Period. Notice I have 2. We need to state that's an integer, plus 1, so that will make 4n cubed plus 2 and minus 1 odd. So again, why is this expression parentheses an integer? Because n is. So since n is an integer, it follows that 2n cubed plus n minus 1 is an integer. And we just got 4n cubed plus 2n minus 1 is odd. And there's the end of my proof. Right? Remember, to show a number's odd, what do you have to do? So I'm trying to show that this number's odd. First, you have to get it as 2 times something plus 1 or minus 1. And then say that the something is an integer. Explain why it's not just say it. Explain why the expression there is an integer. Now again, you could have just, instead of doing what I did, factor a 2 out of the first 2 terms here, said 2 times something minus 1, and then said it was odd. But I wanted to go ahead and do this with the minus 1, doing this little procedure here, because you do this a lot in different proofs. Okay. So it turns out this expression is not just odd when n is odd. It turns out that 4n cubed plus 2n minus 1 is odd all the time, no matter what, as long as n's an integer. Okay, let's look at this next result, number 11. Okay, number 11 says, let n be an integer, fine. If 1 minus n squared is greater than 0, then 3n minus 2 is an even integer. Okay, again, we're in the direct proof section, so that's sort of a clue we want to do direct proof. Now, in an exam, I'm not going to tell you what the method of proof is. So once we go through a few of these methods, hopefully you'll be able to distinguish which one is possibly the best way. So this 11 says, let n be an integer. If 1 minus n squared is greater than 0, then 3n minus 2 is an even integer. Okay, let's do the proof. Okay, so the let n be is that's the universal part, right? Any integer you want. So I'm going to state that, let n be in z, and we're going to assume the if. I'll put that in one sentence, and assume 1 minus n squared is greater than 0. Okay, so again, the first part's taking care of the universal statement. To show universal statements is true, you have to assume it's arbitrary n. You cannot prove a universal statement with a single example. Let n be an integer and assume 1 minus n squared is greater than 0, okay? Well, let's play around with this. This is just, I'm not even worried about the 3n minus 2 yet. Well, if you add n squared to both sides, you'll get 1 is greater than n squared. Okay. Right, add n squared to both sides. Well, remember, n's an integer, not a real number. Okay, it's not, n is an integer. It can't be, it's not, it's an integer, which is a real number, but it's not necessarily, it's not just real numbers. Okay. Now, what integers satisfy n squared is less than 1? Well, if n is 0, we're good. If n is 1, 1 is not strictly less than 1. And, of course, 2 would give you 4. So there's only one solution here. The only possible value for n is 0. Now, if n were a real number, right, n could be a half or 2/3, right, or something like that. There's a lot of solutions there. But, or square root of a half. N has to be 0 because then the only integer whose square is strictly less than 1 is n equals 0. Okay, well now let's consider this. So 3n minus 2 would be 3 times 0 minus 2, which is minus 2, which is even. Okay, if you ever get a number like I did here, we know negative 2 is even. You don't have to write negative 2 as 2 times a k for some integer k to prove even. Right, now if you have an expression, right, like 3 minus 2, or the one we had before, you need to write it as 2 times something plus 1, 2 times something minus 1, or 2 times something to show odd or even. But if you actually get a number, if I got, 582 here, you could just say which is even. We know that's an even number. Okay, there we go. Thus, if n is an integer and 1 minus n squared is greater than 0, then 3n minus 2 is even. That's my little conclusion. And we're done. Okay, so here we started with the hypothesis. We did a little work on it first. Then we got a specific case. And then we used a specific case to finish up. Now, you'll notice I made a comment at the bottom. I said the previous example is silly, as is 12 and 13 in the book. 12 and 13 have the same flavor. The reason is, nobody would ever write this as a theorem. It's stupid. Why would you put let n be an integer and if 1 minus n squared is greater than 0? Right? Because what do these two conditions imply? These two conditions right here imply n is 0. So nobody would ever write this. Remember, when you're writing proofs and theorems, you're trying to make it easy on the reader. This is not making it easy on the reader because you're making the reader figure out that n is 0. So I say how in the notes, how could number 11 be rewritten? I mean, well, even this is silly too. But basically, if n is 0, then 3n minus 2 is even. I mean, again, it still kind of silly, but it's less silly than this, right? Why have all these hypotheses when it simplifies down to a single thing, if n is 0? Okay. Really, the result is actually this is what we proved. The integer -2 is even. That's what we actually showed. So the whole result is silly.